Today we're going to continue talking about complex numbers and we're going to look at some graphs. You need to remember that when you're looking at equations and numbers and things like that, there are ways to represent them as pictures. Just like we have a graph of the line y equals x, and this is a picture, this graph here is a picture of all the solutions where y equals x on our Cartesian plane here, where we have x and y coordinates that are all real numbers. We have this picture for y equals x. We can also take complex numbers and graph them. Now for complex numbers, instead of using the Cartesian plane here like we use for this with x and y, we use a complex plane where we have the real part is on this horizontal axis and the imaginary part is on the vertical axis. If you have a number, let's say we have a complex number, a plus bi. Remember, we have this real part a. So what that means this coordinate here on the real line is a, and we have this imaginary part b, and that means that we went up b on the imaginary axis. So that's how we're going to do it. There's two different ways to deal with this. We can have a point, like we have here, or oftentimes what we do is we go from the origin out to that point and we draw what's called a vector. So we'll talk about several different things about vectors in a little bit, but first we need to discuss some different pieces about the complex numbers. Now, when you have a complex number, we said this was our A length here, and this is our B length here. And we notice that this makes a right triangle, and our distance from the origin to the point that is that complex number, we're going to call that R. Now, we use this number R in several different things, and R is the absolute value of the complex number. And the way we calculate that is with the Pythagorean theorem. We use that information we have from the Pythagorean theorem, and we have that r is the square root of a squared plus b squared. We have the real part and the imaginary part, and we use our Pythagorean theorem to find r. Now this is called the modulus of the complex number. It is the modulus of the complex number. You need to make sure you know those terms so that you can use them. So for example, if we have a complex number, 2 plus 3i, if we want to graph that, we have the real axis and the imaginary axis. So our real part is 2, so we go over 2, and our imaginary part is 3, so we go up 3, and here is that complex number, 2 plus 3i. And we can draw a vector going out here, and that's another way to represent 2 plus 3i. We can look for the modulus, which is r, which is the absolute value of the complex number, and the way we calculate that is by taking the square root of each of the pieces squared. So we get the square root of 13. And what that tells us is this is 2 on the real and 3 on the imaginary, and then this length from the origin is the square root of 13. It's a right triangle, Pythagorean theorem, but the modulus r is the square root of 13 for this example. Now, you can also sometimes look at a complex number, and let's say we have this complex number out here, and we know this is our modulus r, and we know that we have this real part that's horizontal and this imaginary part that's vertical, and it gives us a triangle. So this is our modulus, we know. Now you can also have this angle here, which is the angle from the positive real axis, and it's called the argument The argument is theta. And if you look with your trig that we know that the tangent of theta is opposite over adjacent. So if we want to find out what theta is, we take the inverse tangent of the imaginary part over the real part. And that'll give us our argument. Now, the thing you need to realize is for our modulus, there's only going to be one answer. When you calculate that, a squared plus b squared, take the square root, there's just one answer. But what do we know about angles? We know that if we take the inverse tangent of this, we're going to get a primary answer, but that's not the only one. So you need to make sure you pay attention to what your calculator gives you in reference to what this is. For example, if a and b are both positive, you're going to get your complex number is in the first quadrant here, and whatever theta you get is going to be the right one. But if a and b are both negative, then you should be down here in this quadrant, in the third quadrant, but your calculator is not going to give you an angle that goes like this, is it? Your calculator is going to just give you this reference angle part here. So you're going to have to remember to add pi and get the right angle. So you need to pay attention to when you're calculating your argument and make sure that you're getting the angle in the right quadrant. We always want it measured off the positive real axis, but we need to make sure it's where it's the right one in the right quadrant, depending on what the sign of the real part is and the sign of the imaginary part. Now, the other thing that you need to remember is we can go round and round and round and round and round with our angles. We could have an angle that goes all the way around like this, and it's still the same angle as this original theta. We just added 2 pi to it. So you're going to find that your argument can give you several different answers. So you just need to make sure that you're looking for primary answers when they tell you to, or would you pay attention to what they're asking about your angle, because the argument is not unique. The modulus is, but the argument is not. Now, in our previous example, where we had 2 plus 3i, we had so this is our 2 plus 3i. We found out that our modulus was the square root of 13. Now, if we want to know what our argument is, well, we take our argument is the inverse tangent of the imaginary part over the real part. And when you punch that in your calculator, you get 0.982 radians. And we know that since the real part is positive and the imaginary part is positive, it's supposed to be in the first quadrant. We know 0.982 radians is in the first quadrant because, remember, the first quadrant goes from 0 to pi over 2. So we know that's the 0.982 is between 0 and pi over 2. So we know that it's in the right place. So here's our argument for this particular complex number. Now, sometimes we need to know if two complex numbers are equal. And we've looked at that if we have two complex numbers like this, if we know that the real parts are equal and the imaginary parts are equal, then, so if those are both equal, then we know that a plus bi equals c plus di. The other thing that we can look at, though, is if their modulus, their absolute value, their R value, if those two are equal, if the modulus are equal and their arguments only differ by integral multiples of 2 pi, in other words, by being around the circle multiple times, Okay, then we know that they're equal. So if their modulus is equal and their argument is in the same spot, it only differs by an integral multiple of 2 pi. So we could have an angle here, and we have this is 1 theta for a plus bi, and then we have another one that goes around like this, and this is our other theta. They only differ by an integral multiple of 2 pi. So they're in the same spot, and that tells us that the imaginary numbers are equal. So either the real parts are equal and the imaginary parts are equal, and therefore the whole complex number is equal, or if their modulus is equal and their arguments make it end up in the same spot, then they're equal. So that's equivalent complex numbers. Now, we said that we could have a complex number, a plus bi, and instead of just representing it with a point, we represent it with this vector. Okay, a vector is kind of like a ray. It has direction, and it has magnitude or length, and it tells us where we're going. It has an initial point, and it goes to the terminal point. Now the direction of the vector for a complex number. Now not all vectors are representing complex numbers. We can use vectors to represent complex numbers, but that doesn't mean that's the only use of vectors. When we're using them for complex numbers though, the direction is the argument and the magnitude is the modulus. So this is a vector here. It's got direction, it's going in this direction. It has an initial point. It has a terminal point, which is where we graphed our complex number. And it has a length, r, is what we've been calling it. Now, if we want to name this vector, let's say we call it u. What you do is you write a u, and then you put this little half arrow looking thing over it. And a way to write a vector in vector notation instead of with the complex numbers is you use these arrow looking brackets to label the point it's heading to, its terminal point. So if we have this complex number and we want to represent it as a vector, then another way we could write it is with this vector notation, but it's the same graph situation as when we're just plotting the point. So we have 1, 2, 3, 4, 5. So there's our terminal point, and there's our vector heading to that terminal point. Now, to find the length of the vector, it's just our modulus. It's what we were calculating before. So we have -5 squared plus 5 squared. So that gives us the square root of 25 plus 25, the square root of 50, which is 5 on the square root of 2. So that's how long this vector is. Its magnitude, the modulus of the complex number. We also can find our direction angle, theta, and we said that theta, our argument, was the inverse tangent of the imaginary part over the real part. Now, when you punch this in your calculator, you're going to get that, remember, your calculator is going to give you from -pi/2 to pi/2. So the inverse tangent of -1 that it's going to give you is going to be down here. Your calculator is going to give you theta equals -pi/4. But that's not what we want. We want this theta up here, this black one. So we look at this and we realize that that means we need to add pi to that. And so our theta is 3 pi/4. If you're having trouble with this part where we have to find these inverse, go back and look in your notes where we used inverse tangent, inverse sine, inverse cosine, those kind of things, and make sure you understand how to get the angle to be what you want. Now we're going to use radians for the most part from now on. Degrees only when specified. If it's not specified, then use radians every time. Make sure you've read section 7.2. You've looked over how to graph the complex numbers as a point and how to deal with them as a vector. And you've looked at the modulus and the argument, which is the magnitude of the vector and the direction of the vector. And you know how to find all of those.